Hello, my name is Brian, and I'm going to share some work done with Hilary Finucane and Tamara Broderick on a new approach to making Bayesian estimates in multiple related regressions. Bayesian methods promise to improve inferences by sharing statistical strength across related datasets, perhaps most notably in the context of hierarchical linear regression. However, the standard approach, which treats datasets exchangeably a priori, can be unsatisfactory, particularly when the number of covariates is large, and doesn't actually improve inferences in these cases. In this talk, I'll show how a complementary approach, which treats covariate effects exchangeably rather than datasets, can effectively share strength, both theoretically and empirically. Let's start by imagining we want to understand historical determinants of community-level law enforcement of different crimes. Here, we might want to relate some 100 aspects of community demography to the frequency of arrests. This can be worth looking at to help quantitatively understand how demographics have related to the disparate tolls taken by law enforcement, in addition to serving as a noisy proxy for actual crime levels. If our goal is to understand these relationships, linear models are a clear choice for their simplicity and interpretability. So here, for each community, we could model the number of arrests, y, as a linear combination of d community attributes, x, with covariate effect sizes beta plus a residual epsilon, which we model as normally distributed. However, the data we'd like to look at is actually somewhat heterogeneous. In particular, we can segment it into q equals 4 groups of observations, corresponding to different types of crimes in different regions in the US. And if we believe that the underlying relationships could differ across the regions, we might instead want to use a different model for each region Q, which we'll do by adding a superscript. However, it's not obvious to combine the data from these models, since we don't actually know a priori how similar we think the regions are. In this work, we ask how to best address the differences across regions. Our first option is to hope the differences are small enough that we can just ignore them, pool all the data together and fit a single model. A second option is to treat the regions entirely independently. This allows for differences across regions, but could feasibly make things worse, since cutting down on the amount of data in a high-dimensional problem might introduce too much inferential uncertainty. A third option, which is the focus of this work, is to use a hierarchical model to partially pool the data sets and take advantage of similarities between regions to improve our estimates. However, since we don't have a great sense of how to describe this similarity, we'll have to learn that from the data itself. The standard approach for this would be to treat the 4 data sets as a priori exchangeable. However, as we'll see, this fails when the number of covariates is larger than the number of data sets, and actually provides worse estimates than independent analyses. As an effective alternative in this regime, where D is greater than Q, we suggest the complementary approach of instead modeling covariate effects exchangeably. Before diving into our method, let's take a quick look back at the classical approach of Lindley Smith to see how it compares. And as I mentioned before, this is built on the notion of a priori exchangeability among regressions. Specifically, this means that if we consider all of our regression parameters as big matrix and group the coefficients by data set, then any realization of this matrix would seem just as reasonable if we arbitrarily permuted its Q columns. The relevance of this is that De Finetti's theorem then suggests a parameterized representation of our prior on beta, such that the coefficients of each regression come i.i.d from that prior, conditional on this parameterization. And though De Finetti's theorem does not suggest a distributional family, a convenient choice is the multivariate Gaussian. And this is exactly what Lindley Smith did, and has since been used widely to the point of becoming standard practice. So here, the prior is that for each of the beta Qs, which are D vectors and coefficients, is normally distributed with mean Xi and covariance gamma, where Xi is a D vector and gamma is a D by D covariance matrix. And the basic idea here is for gamma to reflect the covariance and effects of every pair of covariates within regressions, and that by taking these into account, we can get better estimates. However, this approach has some shortcomings. A first one is that this exchangeability assumption can be pretty limiting. In particular, it could be the case that 2 of our data sets are in fact much more similar to one another than they are to the others. And modeling them all exchangeably forfeits the opportunity to take advantage of this. Additionally, the power of this approach hinges on knowing or being able to learn the parameters Xi and gamma. And since gamma has on the order of D squared parameters, this is a tall order when D is greater than Q. By contrast, the approach we suggest for high-dimensional problems is to treat covariate effects as exchangeable rather than the regressions. In our development for how to handle this situation closely mirrors that of Lindley Smith's. Specifically, this approach amounts to grouping the parameters first by covariate and modeling the rows of beta as a priori exchangeable. By analogy, this suggests modeling the covariate effects as conditionally i.i.d and using a Gaussian prior for tractability. So for each covariate D, we model the Q vector of effects, one for each data set, is normally distributed with mean mu and variance sigma, where now sigma is a Q by Q covariance matrix that reflects the extent of relatedness between data sets. So large positive off-diagonal entries correspond to the data sets being quite related. Again, in settings where D is larger than Q, the idea of inferring this parameter is much more reasonable than gamma, since it requires only on the order of Q squared parameters. Okay, so I still haven't explained how to do inference in this model. Before going into that, let's just summarize the presumed generative model. Given these parameters mu and sigma, for each covariate effect D, we draw beta D from this normal with mean mu and covariance sigma. And this gives us our full collection of parameters. Next, for each dataset Q, we sample each of the NQ observations, denoted YQN, from the normal with mean given by a linear combination of the covariates, XQN, for that data point, weighted by the parameter for that dataset, beta Q, and with variance sigma squared. However, this model is actually still incomplete until we've chosen values for mu and sigma. And we propose to choose these with empirical Bayes. That is, we use the observations Y to set these values. In particular, we consider two ways to do this. The first is by moment estimation. So we can construct an unbiased estimate of these under the generative model. And this is easy computationally and turns out to be a good stepping stone for theory, as we'll see on the next slide. The second is type 2 maximum likelihood. So that's estimating mu and sigma by the values which maximize the likelihood of Y when we marginalize over beta. This turns out to have better performance, and while it's more challenging since it's not available analytically, we've derived a fast EM algorithm to compute it. Finally, once we have these parameters, we can estimate beta by its posterior mean. And while posterior inference is a bit more complicated than in the classical setup, because now we have conditional dependencies between the parameters of different data sets in the posterior, conjugacy still gives an analytic form for the posterior mean, which we use as our estimate. To get a more precise grip on how well this approach works, let's take a look at it in terms of risk, first from a frequentist perspective. Specifically, even though we're talking about estimators defined from a Bayesian perspective, since our prior is a function of the data, we can reasonably ask how it does on average for any fixed value of the parameter beta. And for this problem, we'll look at squared error risk, that is the expected value over different realizations of the datasets Y of the sum of squared errors of each covariate effect. Because it leads to a particularly clean and informative analysis, for all the results I'll show, we impose an additional orthogonal design condition. That is, for each dataset, XTX is equal to the identity. And while this is not the full generality that we'd like, under this condition, the problem reduces to a special matrix-valued case of the normal means problem. Specifically, if we look at the least squares estimate of beta, its entries have i.i.d. normal errors. This connection allows us to leverage and adapt a body of existing work for this problem. Additionally, related work, primarily on the non-hierarchical case, allows us to see that some of our conclusions will extend for sufficiently well-conditioned designs. And we expand on these conditions to existing work in our forthcoming manuscript. A final benefit of this condition is that it exposes a deep connection between our approach and the sensible instantiation of exchangeability among regressions by simply applying our estimator to the transpose of the data. Our first theorem, which we derive by looking at analytical expressions for the risk, demonstrates a series of domination results when we have more covariates than datasets. It states that when D is greater than 2Q plus 2, and under the orthogonal design condition, our estimator with moment matching, to choose the prior, dominates least squares. That is, for any value of beta, it provides lower risk. By contrast, in this setting, the analogous approach, which treats datasets exchangeably, is uniformly worse than least squares. And finally, our estimator with our second proposed empirical Bayes estimate of mu and sigma, based on type 2 maximum likelihood, dominates the moment-based estimate. Interestingly, this ordering holds for every beta, regardless of how well it matches our prior beliefs, which is striking since we set out to use this approach only when we expected real similarities between the beta Qs. However, these results still aren't entirely satisfactory for a couple of reasons. First, a lot of pretty strange estimators can beat least squares in high dimensions. So if we'd like to assess if we can effectively share strength, as I mentioned at the start, ideally we can compare to a more intelligent, independent analysis. So in our next result, we compare against applying our method to each dataset independently, treating each problem as a special case where Q is equal to 1. A second limitation is that domination results tell us nothing about the size of the improvements, which we should expect to depend heavily on the unknown parameter. So we'll instead look to quantify any improvement and its dependence on the parameters. Unfortunately, this sort of comparison ends up being super challenging in our original setup. as it quickly reduces to questions about the eigenvalues of non-central Wishart matrices, which are notoriously hard to work with. To obviate these challenges and to further interrogate the high-dimensional setting where we expect this to work well, we consider how the risk behaves asymptotically in the number of covariates. That is, we consider a growing collection of covariate effects. Additionally, we switch from a frequentist to a Bayesian analysis. We let the parameters be random and give them a distribution because it gives us a valid way to reason about a growing collection of them. As such, we now consider the Bayes risk of our estimator. Specifically, if we assume beta is distributed according to some prior pi, this is the expected value of the frequentist risk integrating first over beta. Our second theorem characterizes an improvement in the Bayes risk of our estimator on the whole data relative to independent analyses in this regime. It states that for a fixed number of datasets Q, if we consider a sequence of covariate effects, beta d, distributed independently according to prior pi, then for a large enough number of covariates, our approach provides an improvement. And furthermore, if we let sigma denote the covariance of each beta d, asymptotically, this improvement is tightly lower bounded by a constant multiple of the squared Euclidean distance between the eigenvalues of sigma and its diagonal elements, once sorted in descending order. The significance of this is that it sheds light on this characteristic of the covariance of covariate effects across datasets as an important determinant of how well we can share strength. And while I won't go too far into these details, I'll briefly note that we're able to prove this by first showing that the asymptotic losses of these joint and independent analyses is the same Schur-concave function of the eigenvalues and diagonals of sigma, respectively. And then utilizing the Schur-Horn theorem, which guarantees that the eigenvalues of a covariance matrix majorize its diagonals. Let's now shift gears and look at an empirical comparison on the law enforcement dataset we started with. Ideally, we'd like to compare performance on parameter estimation, but since the parameters are unknown, we'll use prediction mean squared error as a proxy. While this is somewhat indirect, it's a reasonable option from the perspective that explaining variation in the data is what should characterize quality of an estimate in a linear model in the first place. Taking a look at robbery charges in communities in the Midwest, to start with, we see exactly the trend we expect from our theory. Our approach, which I've highlighted in green, gave smaller mean squared error than independent analyses and pooled estimates, whereas exchangeability among datasets did not. Additionally, our approach using type 2 maximum likelihood to choose the prior rather than moments gave a smaller error as well. And while the noise in these estimates owing to small samples makes it hard to distinguish this improvement from noise, when we look at all 4 regions and crimes together and average across them, the differences between these estimators becomes clearer. Let's lastly take a look at performance on a second dataset, this time for fitting a set of linear models of aspects of blog posts that relate to reader engagement. Here, for a collection of blog posts, we look at about 200 attributes, such as bag of words, features, and characteristics of the pages that hosted them, as well as the number of reader comments posted, which we take as a proxy for engagement. As with the law enforcement dataset, this one's also heterogeneous, consisting of long posts, short posts, and posts for which the length attribute is missing from our annotations. And we consider fitting different linear models to each of these subsets. We then compare the same estimators and find the same qualitative patterns of performance. In sum, we've showed that for high-dimensional related regression problems, a hierarchical Bayesian approach, which treats covariate effects as exchangeable a priori and learns the relatedness between datasets by empirical Bayes, can effectively share strength and improve upon independent analyses. And this is part of a forthcoming manuscript, but if you're interested to learn more sooner, definitely just let me know and I'll be happy to share more details or maybe chat about it. Thanks for your attention.